Our second talk will be delivered by Kenichi Yasukata from IIJ Research Laboratory in Japan. And Kenichi will present his paper about a novel in-memory object sharing scheme for virtual machines called ELISA, which takes advantage of Intel's hardware features for improving VM performance. So if you're ready, then please go ahead.
Yes. Okay, so thank you very much for the introduction, and thank you very much for coming to my talk. My name is Kenichi Yasukata from IIJ. So today I talk about our work, exit-rest, isolated, and shared access for virtual machines. So we call this technique ELISA. So this work is done with my colleagues, Hajime Tazaki, so sitting there, and Pierre-Louis Aublin. So thank you. Okay. So this work is I speak about the novel in-memory object sharing scheme for VMs, ELISA. So you can find the paper, slides, and source code and commentary at this URL. So please, yeah, this QR code stays there. So during my presentation, so if you're interested in, please check it out. Okay. So I talk about VMs. So essentially, so we can run multiple virtualized machines on a single physical machine. So the cool part of VMs is like this. So we can partition the physical hardware resource and assign it to a specific guest VM. So in this context, memory isolation is quite important. So what I mean is, in this example, okay, so the blue VM cannot access to the memory of the yellow VM and the red VM. So, but sometimes we wish to share the same memory region. For example, share the I/O device controlled by the some memory, DMM memory. Yes. So for doing this, so there are two existing options. So one is we call direct mapping. So in this case, we simply expose the same memory region to different guest VMs. So this is good because it's fast to access shared memory. So, but the issue is, yeah, like this. So if one of the VM is controlled by the bad guy, so yeah, this shared memory could be used for attacking to the other VMs. So this is one. And another way is host interposition, we call. So in this case, the host provides a specific interface, such as a hypercode, for guest VMs. So the guest VM uses it to request the host to access to the shared memory object. So this is kind of indirection. So in this case, we can achieve isolation, but the issue is, you know, so the request interface causes the exit from the VM context because the request has to be handled in the host context. So, you know, so the exit from the VM context is a costly operation for VMs. So yeah, and it takes a lot of time to switch, and it results in the performance penalty. Okay, so this is a problem statement of this work. So essentially, there are two existing options. However, both of them cannot achieve the isolation and the low overhead simultaneously. So our work is to take the intermediate. So we want to achieve the isolation at low overhead. So, okay, our solution is ELISA, exit isolated and shared access. Okay, so ELISA employs EPT separation. So EPT is expanded page table. So EPT separation for sharing in memory, for isolating the shared in memory object. Yes. So and in ELISA, VM accesses the shared memory. Yes. VM leverages the ePTP switching feature of VM func CPU instruction. So VM func is specific to Intel, and yeah, for accessing to the shared memory object. Okay, so the point is VM func does not cause an exit from the VM context, so which means it's fast. So in the end, so that's why ELISA can achieve the isolation at the low overhead. I think after here it's a bit quick, so let me explain one by one. Okay, so EPT is expanded page table, as I said. Yes, so an EPT is configured by the host and associated with each VM. So, okay, the point one is a VM can only access to the memory listed in the EPT. So, and this is specific to Intel CPUs, and the Intel CPUs allow the host to associate multiple EPTs, and the VM func CPU instructions allow the guest VM to switch the current active EPT from one to another. So in this case, like this. So VM triggers the VM func. Now the context is switched to from the EPT1 to EPT2, like this. So now the VM sees a totally different memory view for its guest physical memory. Okay, so the point here is these two memory regions are isolated because of the EPT separation. So this is kind of similar to the process memory isolation. So the one process cannot access to the memory of the other processes. It's because of the page table separation. So, okay, so another thing is the VM func doesn't cause an exit, and it's fast. So that's why, the VM func can be low overhead. And on our hardware, so it could be fast, 5 times faster than VM code. Okay, so this is ELIZA. Okay, and this is a threat model of the ELIZA, and we do not trust guest VMs at all. And so this green part is a trusted domain for us. And here we put a shared in-memory object and called trusted program. So this is how ELIZA allows guest VMs to access the shared memory object. Okay, so to access the shared in-memory object, the VM first triggers the VM func, and now the context is switched into the trusted domain. So and this can be done by the other VMs. For example, the yellow VM triggers this and switch into the trusted code. The red VM can do the same. So and, after entering this trusted context, so they can access to the shared in-memory object. And here, so this code in the trusted domain is in charge of the concurrency coordination. For example, we can implement the spin lock and so on. Okay, so now after the VM finishes its work in the trusted domain, so it executes the VM func again, and the context comes back to the default non-trusted EPT context. Okay, so in this setup, the point one is the shared in-memory object in the trusted domain is isolated from the untrusted program. So untrusted program cannot directly access to the shared memory object. So this is the point one. Okay, so another thing is the VMs that use the VM func to switch into the trusted context. And as I said, so it's very low overhead. That's why ELIZA can achieve the low overhead. Okay, so the contribution of our papers are actually, so there were two challenging issues, so they're a bit difficult. So one thing was page table maintenance overhead to keep the page tables as the same guest physical memory address in the default and non-default EPT context. As a solution, we present a new technique called APT. And also, actually, there was a potential attack that could be enabled by the combination of trusted and untrusted, combination of VM func and untrusted guest kernels. And we present solutions, so the defense, the get EPT context. And also, we present a new flexible programming model so that we can apply ELIZA to a wide range of the different applications. So but, for these things, please refer to the paper. And so from here, let me report you the evaluation results. So especially, so first we measure the context switch overhead. So this is VM code, represents the host interposition. So this is the baseline. Okay, so now let's say we are running the Blue VM. Okay, so what it does is trigger VM call and exit happens. Now the context enters the host, and it just simply gets back to the VM. On our hardware, so it takes 699 nanoseconds. So this is a baseline. Okay, so this is ELIZA. For ELIZA, we measure time for doing the triggering VM func, switching, triggering VM func, getting back to the default context. And for doing this, it took 96 nanoseconds. Okay, so it means ELIZA is 3.5 times faster than the VM core-based host interposition. Okay, so and this speedup is beneficial for applications, especially which accesses shared memory object quite frequently. And for example, the virtual I/O system is a representative example. And as a use case, so we made so VM networking system. So that is also a virtual system. So this is, and I compare with the host interposition model using the VM code. So this is baseline. So what it does is, okay, so normally the host implements a vSwitch, so virtual switch, so which is a software switch. So, and let's say we are running the VM. And okay, so to access to the shared network card, So it triggers the exit first, and the context jumps into the host, and the host accesses to the shared memory object. Okay, so, and afterwards, it gets back to the default context. So this was the baseline, and for ELIZA, so ELIZA-based VM networking system, okay, so we put the vSwitch in the trusted domain, and okay, so to accessing it, so the VM triggers the VM func, it enters a trusted context, and yeah, going through this trusted context, the VM can transmit packet. And also, yeah, the other VM can also do the same. And also, we can transmit packet in between two different guest VM because this is just a simple virtual switch. Okay, so and we measure the performance. For RX from the network card, we could achieve 54% better throughput compared to the VM core-based host interposition. For TX, we could have 49% better throughput compared to the VM core-based host interposition at maximum. And so, okay, so for the inter-VM communication, we could have 163% better performance. So because there is no limit of the throughput limit of the network card here. Okay, and afterwards we we tested the application, so memcached, so which is based on the C-Star, and the C-Star is a high-speed network stack built on top of the built on top of DPTK, so it's faster than normal network stack. So at the 300 kilo requests per second throughput, it could have a 44% lower latency, 99% latency. So this shows that ELIZA-based networking system can bring performance benefit to applications. Okay, so this is summary. ELIZA is a new in-memory object sharing scheme for VMs. The ELIZA employs the EPT separation and VM func instruction to achieve isolation at the low overhead. Thank you very much for listening, and I am happy to take your question. Thank you very much.